Welcome to Ascendo Reliability's webinar. And today's topic is on acceleration factors. And I'm going to toss out a couple of examples of common ones and talk about some pros and cons of using those things, and just a few hints about how to create your own acceleration factors at a very high level. So it's um, obviously this topic can be very, very deep and very nuanced to your particular circumstance. Um, and sometimes we need to be aware of what questions to ask. And that's really my main aim here is when you're doing accelerated testing, we often think about, well, what's the acceleration factor? And we'll define that, and then when and where and how to use those in a prudent way or an appropriate way. And so hopefully that'll all make sense. Now let's see if I can get my the basic idea here, and is we want to apply a stress, and it could be um, a wide range of stresses. Oftentimes, for accelerated testing, we may apply one stress, maybe two. If you get much more beyond that, then the modeling and the ability to sort out what is the acceleration factor gets a bit muddied. Some people have made strides in some areas, some particular failure mechanisms to have multiple stresses, but typically one. And I'm going to kind of make the assumption that we're applying a single stress to simplify the discussion here a little bit. And I think one of the models examples I have has two stresses, or maybe two of them do. And there's different ways to do this, and but basically we apply a stress. We increase the temperature, we increase the duty cycle, we increase the load, we increase the torque, we increase the power, the voltage, the current, whatever. And but we don't do it willy-nilly. We have to think about what stress we're actually applying and how that affects our product. The intent is to get failures or to get closer to failures. There's a subset of accelerated testing that's degradation testing, where you can monitor the decline of the performance, for example, or the change of a material property over time. But either way, what we're trying to do is apply stress to cause failures to occur, but not just any failure, right? This isn't a halt test, a highly accelerated stress test. We apply single stresses in step stress fashion, and then we apply multiple stresses in a step stress kind of fashion. And we're not exactly sure what's going to fail, which is the point of that kind of a test, is to force things to fail that we previously were not aware of were a weakness. Uh, Here, I'm going to talk about acceleration factors from the point of view where we want to convert this acceleration, this increased amount of stress that we're applying, uh, to our use conditions, to our normal day to day life kind of conditions. And we do that by applying stress, getting to failures, and then backtracking that relationship through an acceleration factor back to our use conditions. And the whole idea is that we learn something. Now, early on, and anybody that's been to these anything related to accelerated testing on the podcast or on these webinars has heard the story of when I the first real project I had that was reliability related was an accelerated test. And my boss walked in and said, we want to find out if this will last for 20 years, and we want to make sure that it has a high probability of lasting for 20 years. And I had no clue as how to do this. And so I went and talked to the chemist. I went and talked to a bunch of other folks about, well, what is likely to fail? What's the failure mechanism? And I learned that I could accelerate that through temperature and also by applying extra oxygen to it because it was an oxidation process. And then we went and did a bunch of testing, and we learned we created an acceleration factor, a model that translated our very high temperature exposures that we were using that would cause failures in the order of weeks, to a model, the acceleration factor piece, that allowed us to say, well, here's the expected distribution out in time in under normal conditions, under regular ambient conditions. And we were able to answer that question of, well, what proportion of units were expected to survive for 20 years. And so we learned something and allowed our business and sales team and the customer that was asking this question to understand what risks they were taking by installing these products and expecting them to last for 20 years. Now, that's a critical point. We can get wrapped around the axle about doing all the math and all kinds of fancy graphs and all kinds of testing. Yet, if we're not actually learning something and using that to answer a question or provide some knowledge, it's really of a little value. And so I start with acceleration factors by making sure we connect what we're trying to achieve to somebody needs to have that information or understand that phenomena so that they can make a decision. Do we ship this product or not? And so keep in mind that I'm going to focus in on acceleration factors, but it's for a particular purpose. Somebody needs to know how many will last for 20 years, for example. Right. And so when do you in the audience here, I mean, many of you are working in the reliability field or in quality fields or in the designs or maintenance fields. When do you need to shorten time? You can use the chat window. What are examples of the types of things that you need to um, my example is a customer wanted to know if it would last for 20 years. And unfortunately, they wanted to know that in 6 months. And so I had 6 months to replicate a 20-year experience. Um, that was shortening time. What other examples when you need to be able to do this? Valve cycling, right? Good one, Arun. Yeah. I think one of the more challenging valve one I found was it was like a safety valve that it's not cycling a whole lot, so the chance of wear out from cycling was very low. Yet the it needed to work when it was needed to work to release pressure on something, and its failure mechanisms was like corrosion, and it would stick. And so it was a focus in on how do I shorten the time to know if it's going to corrode and get stuck, and how much corrosion causes enough of it to be stuck, kind of thing. And so there's some challenges there. Where do we let's see, expected product life, warranty. Um, so Brian, you conducted a significant accelerated test for a gearbox. That's good stuff there. All right. Vibration amplitude of the proper frequency. Um, let's see what else is out here. Evaluating process changes. Yep. To know if you made a change and it helps the reliability performance or not, but you don't want to wait the 2 years or 5 years or 10 years. Connectors mating. All right. Good. All excellent examples. Good, good, good. All right. So a little bit of basics first. The definition is basically I look at it as it's a way to take the performance of our product, the time to failure distribution, for example, say the first fifth percentile of that distribution or the median point of that distribution or whatever it is, uh, under high stresses, and I want to translate that or convert it in on a plot. It's shift that response back to use conditions. So if I'm testing something at 200 degrees Fahrenheit, or say 200 degrees Celsius, and I want to operate it at 25 Celsius, well, that's what an acceleration factor helps us do, if it's appropriate, right? And we'll get into some of that, but basically, it's just the ratio of what is the translation from the accelerated stresses to the nominal stresses, and then how do we convert that into a meaningful result. So pretty straightforward. I think it's in a dozen different books out there that are around. Right now, the let's one quick example of this, and probably the simplest one, and this is where I get to try out my find my cursor, is try out the annotation here. Is if I've got a timeline, and I'm going to use my favorite example of a toaster. And if every morning I make, say, two slices of bread converted into toast, and it on a daily basis, I'm just putting day time hacks here, right? And if one of the assumptions we make in designing a product is, well, how often does somebody use a product? Now, this works for things like a toaster that gets used once a day. It's not so good. It's not a useful way to do acceleration if the product is used 24 hours a day and 7 days a week, say a server uh, on the internet somewhere that is always available, always on, always moving bits and bytes around. So it wouldn't work there. But it's something that's not used all that often, say a door on a vehicle, for example. We're not opening and closing that 24/7. But if we're experimenting with the ability of the latch to keep the door closed, well, then that's 24/7. It's closer to that phenomena. But if we're investigating the hinge and alignment and its swinging motion, that's a different duty cycle. So it's time compression is one of the easiest one to comprehend. It's just you're going to use it more often, right? So the second part of this, my accelerated test, is another timeline, but it's in under um, say I'm going to use high here, and I'm using my mouse to draw here. Unfortunately, I didn't get all organized to, and this is nominal to get my fancy pen. Now, how this one's obvious. I won't even ask. So I'm just going to use it more often. I'm going to make toast more often. Now, what is one thing to keep in mind if I use it more often in order to replicate the amount of, I don't know if I got the same number here, the same number of problems, or defects here, or cycles, I should say. I just do it quicker. And so instead of a week of cycling, I can do that in an hour, for example. But what's one of the major considerations here that you need to build up? Yeah, and Bill's on top of it already is the heat buildup, the cool down between uses. Yeah, exactly. Now, why is that? Right? If I don't let it cool down, and I'm thinking that my underlying failure mechanism is this heating coil has an attachment to the frame, and that when that metal heats, it expands. So it's got to move in some fashion. So if it's not strain relieved correctly, if it's not attached appropriately, um, it's likely to get some metal fatigue where that motion is occurring. And so if I don't let it cool down, I don't get the benefit of that thermal cycle. The other way to think of it is that when I make a slice of toast on Monday morning, I make it heats up and ends, and it completely cools down over 24 hours. But we're trying not a simple thermocouple or a temperature reading of it will know when we've come back to ambient temperatures. And if you're really impatient, you can put it in a cold chamber during the cool down cycle, for example, and shorten that time. And you can work out from some engineering and observations is what is the appropriate cycle time so that I replicate the same failure mechanism, but I just am able to do it faster. And it's one of the key pieces of these acceleration factors. And I've seen this a number of times. Another example was a wristband fitness tracker type product, and it was flexible. They were trying to make a circuit and batteries and everything else of that in it that you could put it on and off like a bracelet. It would instead of like a watch with a hasp or a clasp to it, you could basically bend it open and it would then allow you to get it around your wrist. and it would fit many different sizes that way. And so the team decided they had a little mechanical device that took the two ends of this. I'm using my hands, I know you can't see me. And they would extend out to the full range. It would stretch out this band almost flat, and they figured that's worst case, and then they would let it come back, and then they would stretch it all the way out and let it come back. And they found that it took 12,000 cycles before they had electrical failures, before the system stopped running. And it was usually a wire break of some sort. And they said, all right, we're good. We don't expect people to use it at worst case for that many cycles. So if don't bend it as much, it should be higher than 12,000 cycles. And that was a critical mistake. They made that assumption. And so we said, well, let's run the test. How do people put this thing on and off? And what's normal case? And let's run that to failure. And the, otherwise, we don't have a way to compare the nominal use to the high stress use. And so we got a bunch of people standing in a circle, and one would put it on and off 10 times and hand it to the next person and go around the room, and pretty quick they were up to like 4,000 cycles, and it failed. So the nominal use was more stressful than what we thought was the high use test. So in time compression, it's an understanding of the failure mechanisms is one of the critical factors, so that the applied stress actually excites that failure mechanism. Now, what changed from the mechanical extension and retraction of this device was that it was linear. It was always exactly the same, and it happened to be just a flat run. Whereas people put it on in different ways, and it would twist. And it was that twisting motion that added just enough strain on these wires to break them fairly quickly. And it took a lot of iterative processing to figure that out and get it right. And then they were able to create a test that replicated the understanding of the failure mechanism that included that twisting motion that was similar to the way people really did it. But the idea was is that I'm just doing the same number of cycles of what I expect to be done in nominal use if the applied stress is consistent with this type of stress that's causing the failures in regular conditions. And then it's just the ratio of uh, if I've got 5 cycles in nominal use and I can test 5 cycles in an hour, that is just the difference in time. Instead of a week, it's an hour. So it's 1 week is related to 1 hour. And it gives me that ratio. And I can convert up from stress or down from the high stress and move forward with that compression. So that's a very simple example. Let's see if I clear my drawings. I'm learning the hard way that if I am not able to advance the slides unless I get rid of the annotations here. So let me do another quick drawing. Let's see, I'm going to take a look at questions here before I get too far. Yeah, and Bill, you're exactly right. Is the cycles to failure, the rate matters, and the toaster is a classic example. Is that if I don't let it cool off, I don't get as much of a delta T, a change in temperature. And if the change in temperature is what's causing the actual mechanism to manifest, then that matters. Um, and sometimes it's if you understand the failure mechanisms, you can accelerate very fast. Yet you do need to be cautious about the byproduct of heat generation. I think that's independent of toasters where there's a lot of heat and that's what's causing the motion. Bending metal does depend on the rate to some extent. I'm going back to like Kaufman-Manson equation, and I have a superset example of that a little bit later. We can talk about it some more. But the idea is that the fundamental idea here is that you need to understand the mechanism. What is actually failing, and what is how is the stress causing that failure to grow or happen? Let's see. Alan, let's see. I'm experiencing some fatigue failures on leaching tank agitator. I'd like to know which approach, test, or any procedure I can use to solve this failure mode, even be able to predict this failure. Fatigue failures. The the quick answer, and there's not a quick answer, is if you understand that it is a fatigue failure and you're able to monitor the change of that fatigue over time, take a look at either Bill Meeker and Meeker and Escobar's book on oh, Bill, help me out with the title of your book. I just call it the Meeker Escobar book. Um, it's the statistical reliability, but you have a lot of test stuff in there, and I believe you have a good chapter on degradation testing. And then there's Wayne Nelson's book, Accelerated Testing, that has a whole chapter on just degradation. And it's a way to monitor that data. The key piece of this, though, there you go. Thanks, Bill. Statistical methods for reliability data. The, the idea is that if you can monitor that degradation, it might be an increase in vibration or a change in performance or crack growth or whatever it is. If you've got some way to monitor that degradation over time, then you can model that. And then you can, for example, do different types of designs or welds or whatever it is that's underlying that cause of that degradation, and experiment fairly quickly with what is going to be robust enough to avoid that particular failure mechanism. Now, of course, this gets more complicated pretty quick because as you change designs, you may be changing the nature of the failure mechanism underneath it. So it's being a little bit careful with that, Alon. It's but the idea is if you get fatigue damage, then the critical piece is, can you measure it? Can you monitor the performance or crack growth or some other feature of this so that you can tell, and then use that as a degradation path? And I find that if you can do that, there's all kinds of advantages. And then you can run experiments and do other things to understand how do I change this to be more robust for that failure mechanism in a meaningful way. So obviously there's way more comments and questions on that, but it's a good idea to take a look at degradation testing. Yeah. So where to get information on the right acceleration factor? That's the hard part, and that's why I wanted to talk about this sub, is that there's I've run into a number of people that think, oh, I'm just going to put my whole device in a chamber. I'll elevate the temperature. We expect it to work at 30 degrees C ambient, and I'll put it at 60 degrees C ambient. I'll use the Arrhenius rate equation and assume an acceleration or assume a activation energy. And then I can calculate the numbers, right? That's not a problem. Our Excel and our basic calculator, we can sort that number out. But is it meaningful? And that's I think the core of your question here, Sub, is that there are a lot of sources. But if you just open a book and say, oh, here's an acceleration factor, we're testing with temperature and humidity, so I want to convert that. Well, there are models out there that convert stresses of temperature and humidity to an acceleration factor. Yet the critical part is that, do you have the right failure mechanism for that acceleration factor model to apply? Does it make sense? Um, and I'll get into a couple of examples of that here in a minute. So let me explain one of these, this idea of acceleration factor from the point of view of uh, a oops. Let's see if I can get my drawing here going again. Nope. Let's see. I got to get my cursor back for whatever reason. All right. Technical problems here. Oh, let's see how I can get out of this. One of the features of this package I'm using is it hides the cursor, which is really hard to then know where your cursor is so you can push a button. All right, come on. Let's try. I'm getting my little beeps here. All right. All right. There we go. Got a cursor back. Get rid of that. All right. Now I can do my drawing. There we go. So let's just draw, figure out where my cursor is. If I've got a cumulative distribution function, and I'm just going to use just a CDF in general. So I've got some fancy scale on the vertical axis that gives me the probability of failure from 0 at the axis up to all of them fail at the vertical. And on the x-axis, I've got time. And if I run, oops, way over there. If I run a test and I get a nice straight line and I'm happy with the data set that I have, and it's failing pretty quickly. And this is under my accelerated stress. I have an amount of stress. I get the failure mechanisms I expect. It follows a nice distribution. I get a nice straight line on my CDF plot. And what I want to know though is how will it behave out here in normal use conditions, right? Which if I have an acceleration factor model, it's telling me that this is this shifting of this curve to the right is from that acceleration factor. And it's making the assumption that the failures behave in reaction to the stress in the same way that they will under lower stress. So back to that metal fatigue on a toaster. If I don't let it cool enough, it will go through many more cycles of making toast, for example, or of the heating cycle. Because it's not cooling down, it doesn't accumulate as much damage per cycle. So it's fundamentally different under the high stress than it is under a low stress. So these curves will, one, they'll not be parallel, but two is um, or they may be parallel, but they will be describing a different set of conditions. And so one of the fundamentals of acceleration factors that there's a whole slew of assumptions underneath it. And the fundamental one is that the failure analysis and the phenomena, the physics and chemistry is what's happening under the high stress conditions is the same or close enough for us to be accept it when it's under nominal use and stress. And so failure analysis and these kind of things is critical to understand that are we getting the same phenomena? Now, some of the underlying uh, um, assumptions are, or is that other failure mechanisms won't cloud our high stress one, or that this failure mechanism will not be masked by some other mechanism that just doesn't occur as quickly or in the same manner when I go into high stress. So there's way more than I can talk about here, but the basic idea of the acceleration factor is how does this distribution shift and what's the magnitude of that shift? And there's a whole slew of assumptions underneath that. All right, so let me get rid of my drawing here. Yeah, I don't like this annotation. I'm going to try a different one next time so I can. Because it's not letting me see the cursor. Huh. And it's one of my. There we go. Sorry about that. All right. All right. And I just mentioned the number parts of these assumptions is really pivotal that you understand the underlying failure mechanism. if we're changing something in manufacturing, um, and want to see how it goes, one of the caveats is that is the applied stress, which we if let one of the assumptions I've seen early on in my career is that we have a problem, and we know that it has this coefficient of thermal expansion issue that as it heats up, it expands and it creates a force on a joint. This is a real example. And the problem was is the joints were coming apart. It was disassembling itself with thermal cycling in pretty quick ways. So they were experimenting with different ways to make attachments that would accommodate this motion, but still maintain the structural integrity of the device. And so we made a device that allowed them to quickly apply the same amount of strain or force on this joint without having to heat the whole mass up and cool it all down. We were able to do it mechanically to replicate that. The issue was is that the the force was applied so fast that it changed the way the structure moved and responded to that motion. As this, it was a polymer siding basically, and as it heated up, it softened. And so in normal use, it would soften and it would change. It would its dynamic motion was different than when we did it mechanically with a cold piece of plastic. And so the ending results of experiments using this rapid force device we made um, didn't really apply to when it was warming and cooling in its actual state. It got us closer to a good solution, yet it became clear that it wasn't really mimicking the real stresses. So it allowed the mechanical folks to figure out a couple different strategies for doing this. And then we still did the thermal cycling testing to get closer to what the real use conditions are. So one of the gotchas I've learned the hard way a number of times is that just because you can accelerate the stress, there's almost always a bunch of other caveats and little elements of this that need to be thought through from a detailed engineering perspective. Is what is if I'm not completely replicating the actual use conditions, I'm taking more and more risk as I move further and further away from the actual conditions. If I move to a coupon sample of something versus the actual product, I'm making assumptions. If I'm moving uh, to a high cycle one, am I building up too much heat? All of those kinds of things start really making a big deal on how we can interpret our acceleration factor. And so even if you pick one out of the book, all of these same thought processes still apply and all these assumptions still need to be thought through. Yeah. So Deanna, if the if in that CDF plot, I'm not going to try redrawing that, if they're not parallel, then there's something else at play here that's altering the slope of your curve, for example, or the shape of that curve. So when early on, I did three different temperature uh, settings to do an accelerated test, and they were slightly different behaviors. And it was the question was, well, what's causing that? What is underlying this change in the way this failure is manifesting itself? In talking to the chemists, in this case, I had a polymer system that was oxidizing, and they said, well, it's not like solder joints that are eutectic, where it means that they melt all at one point. Polymers tend to melt over a very broad range. So parts of it start to soften or melt at say 50 C before the transition temperature. And so it starts to soften and soften and soften. And so I was getting close to the upper end of that area where the weakest part of that polymer chains were starting to soften. And so once we took that into account, which was dangerous because we were not operating this product anywhere near the softening points. So we factored in that change in behavior into the modeling, and it accounted for this chemical process that was going on. And we did some other tests that stayed well away from that, which they took much longer to do. But it allowed us then to say the failure mechanisms and the models we have are still appropriate. But if you don't get parallel lines on that Weibull plot, it's one of those cues that we're not done yet. There's something else at play. There's some other phenomena that's affecting the rate of arrival of these failures. All right. So some of the elements of this, and I've talked about this one at length. And so why is knowing the failure mechanism important? And and it's leading me up to another question, which is, can you do an accelerated test on, say, an entire laptop in a meaningful way? But why do we need to know the failure mechanism? Yep, good. So you don't it helps you get the right model. That's exactly what I was looking for. It it is so you don't overstress it, right? Failure mechanisms, then say if it is temperature and it was my polymer system, one of the first things we knew is that we didn't want to melt it. And so we thought we were far enough away, but I wasn't a good enough polymer scientist to know that it softens quite a lower, quite lower and than its transition temperature. And so the idea here is, in any accelerated testing, is start with the failure mechanism. And if you don't know the failure mechanism, start with a halt test so you can find out what's failing, for example, or use some other engineering work to figure out what is the underlying failure mechanism. And because if I understand the mechanism, then it you almost always then presents, well, now we know what to do for the stress. It gives us a pretty clean picture of what causes that mechanism to occur. And it's that level of understanding that allows you to get into selecting or creating a acceleration factor. But without the mechanism, we're pretty blind. We're not really sure what's happening. And then if that's the course that somebody is taking, is you really got to get to failures so that you get some understanding of what actually is failing, and then sort out how to interpret that and understand it. Um, but it's absolutely important in my mind, and my advice to you is that if you're looking at an acceleration factor, is don't start with the acceleration factor, or don't start just because you have a temperature humidity chamber and there's an international standard that says use 85C and 85RH and that's your test, and then go look for how to interpret that. Is start with, well, how does your product respond to that stress, and what is the failure mechanism that you're interested in? And why it's important to me is, and I wrote about it earlier this week, is you don't want to commit the type 3 error. Now, many of you have heard of type 1 and type 2, the producer and consumer risk for sampling. The sample gives you a false positive or false negative just by chance of selecting your samples from a population. Well, type 3 error is solving a problem very well. You might run a perfect, beautiful experiment for accelerated testing, yet you might be stressing the wrong, using say temperature at a fixed rate when you're really interested in metal fatigue and you need thermal cycling in order to excite it. See, if you interpret, oh, this metal doesn't fatigue, if you just hold it at high temperature, you could do a perfect experiment, but get a really bad result because it doesn't apply. It's a type 3 error in my mind, where you are solving the wrong question, essentially. So that's why we need to know the mechanism. And a couple of you chimed in right on it. Now, the other thing that happens with acceleration factors is that we're extrapolating. Now, my to my chagrin, I heard from a couple of younger engineers the other day that um, they didn't have to take a statistics class when they're in their engineering programs. And it wasn't in my day, it wasn't everybody's favorite class, although I did enjoy it, and I ended up going back to school and taking a lot more stats. But the idea is that in vast majority of classic statistics, and I'm thinking the normal curve and hypothesis testing and basic regression analysis, is that we are taught basically don't go beyond your data. So if I'm testing at 10 degrees and 20 degrees and 50 degrees, I know something between 10 and 50 degrees. But if I really want to know what happens at 75 degrees, and I use a dotted line to extend that extrapolation or that regression line, I'm extrapolating. I'm projecting out beyond where my data is. And the interesting part about acceleration is that we often do that, right? We're, in this case, we're using high stresses in order to shorten time, and then we're extrapolating back to nominal stresses. And it's, think of it as that we're using a week or 6 months of testing, for example, and extrapolating out to 20 years or 10 years or whatever your model is giving you. Now, a lot can change beyond your data. As I found out early on, is that if I get too close to the softening point, I get a different behavior, is that these lines aren't parallel anymore. The CDFs, the nature of the failure arrivals changes. And so there's something changing as I go up in stress. So extrapolating back is, well, what else is changing? As this gets colder and colder, does that fundamentally change how it behaves? And so we're making, the closer you can run your test to the nominal use conditions, the better, right? Is you're taking less and less of a risk. Your extrapolation becomes smaller and smaller. And so it's, I'm thinking of it as the analogy of standing on a diving board, right? If you stand near the anchors of it, it doesn't move very much. There's not a lot of variability there. But if I move out near the end of that board, it will flex quite a bit. There's a lot of variability there, right? Now, in there, we know, we kind of have an understanding of the board and how it behaves, and we use that phenomena ex, to extrapolate ourselves, so to speak, off into the water. But that's not always known and well characterized. So the less you have to extrapolate, the better. And but understanding that you are going into an unknown region based on where your data set is puts a lot of faith in your model. So selecting that acceleration factor in those models is important because of the amount of variability that may occur that we won't be able to see until our products actually experience their normal life. Right? We have lots of limitations on this thing, right? And I mentioned a number of these things. Um, Back to my early on experiment, is this polymer system had a second phenomena. It was one of these things that was a degradation process, and we were using just a straight line. We assumed that it would degrade continuously through the bulk of the material. It would just continue to oxidize, and it would continue to change the resistivity of our product in a straight fashion. And even though we were using, log scales to make it straight, it would just be consistently apply time or stress, and it would change in a known way. Well, that didn't happen. As we were plotting these things, that curve flattened out. Instead of coming down at, say, a 45-degree angle in its changing of resistance, it started to flatten out, and it changed less and less over time. And so if you ran the test for a very short time, it projected our failures would happen very quickly. But if we left the samples in the oven for a bit longer, they didn't follow that line anymore. They broke off of that. And now we're projecting they would last a bit longer. And the longer we ran, the longer it would project it would last. And so the modeling we were using was assuming that linearity, that it would be a constant rate of change with time and exposure to a particular stress. And that didn't happen. And so part of the process of looking at your accelerated testing data is to challenge all of these underlying assumptions. And so if your model is assuming it would be a straight line and it's not, something else is going on. And to make a long story short, in that other case, it was oxidizing. And that process, that chemical process, reduced the ability for oxygen to get deeper into the bulk of the material. So it was creating a barrier to further oxidation. And it took some chemists and some clever experimentation to prove that. Yet, if I would have just assumed the model was right and ignored this curvature, I could have picked two data points and really said it's going to fail in 6 weeks, or I picked two different data points that are a little bit further apart in my testing. Now it lasts 70 years, but it wasn't accurate to what was actually happening in the data set. All right, so let's talk about a couple of models. Black's equation. So if you run into an acceleration factor model and it doesn't tell you where it's used or what failure mechanism it applies to, you need to ask a ton of questions and figure out, where did this model come from. So in this particular model, um, the this is, I'm looking at electromigration, and it's within the aluminum wires that are built into semiconductors. So it's very specific. And as we move to copper wires and other types of metals and semiconductors, this model had to be updated and recharacterized to understand exactly what the expedient, is it the right model anymore or not. But if you're doing aluminum metallization and CMOS semiconductors, and electromigration is the phenomena where the 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 atoms in that conductor actually, due to current flow, think of it as rocks in a river. If you get enough current, those rocks will shift and move. And what happens is that it'll thin out one section, which then makes it go, it's like a rapid then in a river, instead of a nice soft flowing river to float down in this nice summer afternoon. It's a raging torrent of current going through that spot, and it moves more and more rocks out of the way, more and more atoms get moved. And so it thins one part out and builds up in another area. And that's electromigration. But this model only really applies to aluminum. Now, the form of this, the J, the Juliet's terms, is the ratio of the currents. And then the other part is, you're very familiar, I'm sure everybody here is familiar with that, as an Arrhenius type of a format for acceleration factor. Well, the current, in this particular model, the Black and colleagues sorted out that if I do just current, it explains almost all of it. But I'm going to add this temperature piece to it so that I can accelerate it a little bit more. And I don't know the details of why they use temperature to do this or what the chemistry of it is. And if I'm doing $1 million experiment, I would want to understand that. Why are both these terms here, and what are the phenomena that they affect? But it has the activation energy, and it has N, the superscript minus N, which are critical to this particular model. And going to a table of books and saying, well, I'm using copper instead, and I'll use the aluminum metallization factors on this, that may or may not apply. So tread carefully there. So going back to the papers on these guys and understanding where this got derived from and where it is, allows you to understand, does this apply for my circumstance? Right? And if it doesn't, well, that may suggest that you either need to look for a different model, or you need to run an experiment that allows you to estimate these fitting factors, this activation energy, hopefully from some fundamental understanding of the chemistry involved. And then also this exponent, this minus n. Is this appropriate for my particular circumstance? So it might be a good general form to fit lots of different curves or different phenomena, yet the Black's equation as published gives you values for activation energy and N, yet they may not apply for your particular circumstance. So challenge the understanding of the model to your particular circumstance by understanding the failure mechanism that it applies to. Peck's relationship, he was clever. Um, I know, drawn a blank. It was in the 70s or 80s, is somewhere in that realm. Electronics um, was moving from metal cans to encapsulate a transistor or some uh, bit of electronic wizardry to keep it from contamination and eventual corrosion and failure. That it would, people like Motorola and others were encapsulating their electronics in an epoxy, a plastic. And so they would overmold the lead frames, the little wings that come out and that you attach to the circuit board. They would attach the little device, the IC or the chip or device or the transistor or whatever it was to those lead frames, and then they would pot it basically. They'd pour a bunch of mold, they'd mold some plastic or this epoxy compound over it with the intent of sealing it so that the epoxy to the metal would form enough of a seal to prevent the transmission of humidity, primarily moist air, into it that would then cause corrosion. Once you add a little moisture to an electric field, it's a ripe area to cause metal to move. And so it's one of those things to be aware of. The relationship, though, was based on the clever part. What I think he did is he looked at hundreds of different tests that different companies and within his own organizations were doing to understand, is this epoxy actually preventing this corrosion failure within our devices. And so it used slightly different epoxies, slightly different processes across these different realms. And then he just fit. He did a regression to said, I can describe this phenomena in almost the exact form as Black's equation, right? There's the Arrhenius piece of it, and how I'm using relative humidity and an exponent of n. But that activation energy and that n are fit or are determined because they had all this data that they were able to analyze and do a regression fit to it, and they came up with these fitting factors basically. But if you're using temperature and humidity and it's not looking for how effective is a seal from epoxy to metal to avoid corrosion on electronics, if you're using that, say, on a solar panel, or you're using it in a gallium arsenic circuit, or you're using it on a solar panel or on paint, I've seen this temperature humidity test used on so many different products and systems. And temperature and humidity are great stresses to all kinds of failure mechanisms. Yet just grabbing Peck's equation with his published N and activation energy is absolute folly, right? Grab Black's equation instead. They're different. And but they're both tied to a specific failure mechanisms. So once again, I'm stressing that. Understand the failure mechanism and then get the model that applies to it. Now here's one that's a little more complicated. It's called Norris-Landsberg. This is for solder joint fatigue. And it's based on the Coughlin-Manson relationship that if I uh, stress metal, basically load and unload metal, it will fatigue. And that's a pretty general form model, and it really works well for a wide range of metal fatigue type problems. Now, solder joints, um, it also depended on how high of a temperature I went, how often I cycled it. And then there is this temperature factor. There's that Arrhenius equation bit in there again. And again, this was done with lots and lots of testing. And I worked at Hewlett Packard when the lead-free solders were becoming more and more required out of the European Union, and then it just became standard. But we had 50 years of experience with leaded solder, and this equation fit that really well. And we had long-term studies and lots of test data that said this was good enough for lead-free or for leaded solder. And the question was it good enough for lead-free solder? That the fundamental chemistry of that solder was changing, and the nature of the failure mechanism also changed. The path of these thermal cycling stresses essentially changed in how it manifested damage in the SAC solder, for example. And so the question was, what fitting parameters do we use? So we use variety of different stresses and different dwell times and different sets of experiments in order to determine what these equation, what was the right activation energy N and M in order for this to be a useful phenomena or model for us anymore. But it's one of those steps that there are models out there. There's hundreds and hundreds of different models. The physics of failure has produced a lot of insights and understanding, but it can be done empirically in running a very sophisticated sets of tests with multiple stresses, or it can be done um, by collecting lots of other life tests and doing the analysis on it. Um, but the basic point is that a lot of that prior work really only applies if you match the failure mechanism. So hopefully that's coming across. So is there a model for an entire system, say a laptop? Now, my short answer is no. Now, if your system is such that it has one dominant failure mechanism and the type of stress is really applied to it during normal conditions, that's why it's how it's going to fail. That's the most likely path to failure. And then you can run an accelerated test on that system with appropriate stresses for that dominant failure mechanism, and you may get a useful result out of that. But the idea of, say, a laptop, well, there's CMOS technology, there's battery technology, there's power supplies and dozens of different kinds of components and attachments. And then there's a wide range of stresses. If I slap my laptop down on my desktop and it never moves, the chance of dropping it are much different than if I'm running through an airport every day. And or it's in my briefcase and it gets dropped, or it's being handheld and opened and closed as I'm walking down the office to a meeting or something. Remember back when we used to go to offices? The idea is that every system has lots and lots of ways it can fail. And on occasion, we identify a dominant failure mechanism. And it's a great way for us to then run it as a system because it's as close to its use conditions because it's all together. But it makes it more difficult to isolate failure mechanisms. If I happen to be applying stress that accelerates multiple failure mechanisms, then which model do I use to translate those failures that were all different? And then it just muddles the whole thing up in order to really get a good understanding of it. And it's a real challenge. And oftentimes why we do accelerated testing on a particular component or a particular attachment or a particular phenomena or element of a product so that we can isolate it and characterize it carefully. Because when you put it into a system that has many competing failure mechanisms, it gets much more complicated. Usually, sample sizes just for simple accelerated tests are more than most people want to deal with. Now you add, say, 4 or 5 competing failure mechanisms. Well, now it gets even more complicated and more samples. So one of the questions I'm seeing in the question tab, and I don't have a really good answer for this other than don't do it, is if we don't know the exact activation energy, can we use a estimated range of activation energies and then get us an upper and lower value of it? I understand the logic of that approach, but the idea is that if I follow that approach and one end of that range, I would say ship the product, we're good, and the other end of that range, it's oh, this is a disaster, it's gonna cost us a fortune and failures. That it doesn't help you. Now, if both of them are saying no, it's not good enough, or both of the results are it's good enough, then I think you have to think through all the possible outcomes. It may not help you. And then you'll know you need to go do more research to figure out what is the appropriate activation energy. The hard part is that sometimes you get this a phenomena where you adjust the model to find the answer you want, and without having the actual use conditions and evidence or ways to verify your accelerated testing, it's too tempting to adjust the model to find the answer you want. So be very careful about making assumptions. But the logic of if I know from past research and stuff, they're giving me a range of activation energies or these fitting parameters, and it doesn't change my result, the decision that we're going to make, then you're in good standing, I think. It's not as robust as actually understanding the failure mechanism. But the concept is that sometimes it doesn't help. The range of activation energies gives you a wide range of results, for example. And now it comes down to which one do I want it to be, which is hopefully is something to guard against, to be aware of. All right. So I'm going to go over this real quick. Um, the basic idea of creating an acceleration model, and so acceleration factor model, in the simplest method that I know of, is run three different stresses, right? And so if I'm just using temperature, let's say I'm looking at a chemical breakdown of a paint or a coating that I'm putting on a surface, I would make up a bunch of samples. I'd put them in three different temperature ovens. Maybe it's UV that I'm using, different intensities of UV, and track the time to failure. I would get three different distributions or three different time to failure distributions. And let's say they're Weibull distributions, because I like Weibull for no apparent reason, but I get three distributions. And the nature of the failures is the same. I can check that through failure analysis and understanding how the phenomena is failing. Now I've got three distributions. And this is where I wish I understood this. Let me try a different technique real quick. Try this one. So in one step, I've got my high stress, a medium stress, and a lower stress in my testing. And this is time. And what I'm after is my use conditions. Let's see if I can do a dash line here. Right? We don't know this one. We didn't test this condition, say this 25C condition. But I do know the difference between this temperature and this temperature, the distance, the shift that actually occurred. And I can think of that difference, that shift, as an acceleration factor. And then what model describes that shift, but also describes that shift and describes this bigger shift between the outer one and the inner one. And once I create a model that describes these shifts, these acceleration factors between these three distributions that I created at three different temperatures, then I extrapolate to my use conditions with the hope that I didn't violate any tenets of how the failure mechanisms behaves when it's under higher stresses to lower stresses. And there's a number of different models and forms of equations that help you do this, but keep in mind that what we're basically doing is saying at high stress, this is time on this axis, and this is stress on the vertical axis. When I go to high stress, it doesn't take very long for it to fail. And if I go to low stress, it takes longer to fail. And it's this regression here that I'm basically saying is my relationship between these higher stresses and the low stress. And so I'm extrapolating back to my use conditions, or I should say down to my use conditions in lower stresses. So one way to do it is go after the recommendations I often see are for three um, stress levels, and it allows you to see if it's a linear relationship between the change of stress to the response that you get. But it also, if one of them is way too high or you don't get any failures, you still have 2 points. And if you get 2 points, you can draw a straight line through it. Three, now you can see if it really is a straight line. And that's kind of really stretching regression analysis quite a bit. More would be better, but oftentimes we're constrained by just the uh, the, the finances and time involved with doing that. All right, let's see if I can get here. The other part of this is that the regression analysis is really two steps. One is we're fitting a time to failure model, right? The Weibull curve on that last description. But then we're also comparing where those where those curves land on our cumulative distribution function. And then we're modeling the, say, the fifth percentile, if we're interested in when 5% of our units would fail. Then we're modeling the time it takes to get to that failure and on a, hopefully in a simple regression, a linear, nice straight line type of regression. More sophisticated in what uh, Bill does in his book and Wayne does in his book is talks about, well, how do you do this regression all at once? How do you take into account these three different time to failure distributions and their spacing in one model that then allows you to do the extrapolation back to use conditions and fit all three lines simultaneously. Now, the last piece I want to advise is in this analysis is plot your data. Take a look at it. Is your data in is it make sense to where the regression analysis draws the lines? Right. A couple of quick tips is do the research, read the papers, understand both the failure mechanism, physics, chemistry, or whatever is phenomena is occurring that causes the failure to occur, and understand the statistics. We're pushing the edges of what most people learn in school, of what's allowed and not allowed and how it works and what assumptions we're making. And the last one, and I learned this one the hard way, is measurement error can really be a pain. So minimize it, pay attention to how you're making your measurements. So with that, I ran over a few minutes. I know in our world today that probably means we're halfway into our next meeting, but with that, I want to say thanks. And if you got any follow up questions or thoughts, I'll stay on the line and stay on the chat window and questions tab. And I want to thank you for participating. I got a bunch of cool ideas and stuff here. And so, once again, thanks for joining the webinar. We're going to post this hopefully within a day or two, and it'll be available if you want to replay it. I do have a PDF of the slides, and that'll be up on the site also, along with these. Um, an hour is by no means enough time to really talk about acceleration factors, but hopefully I made a couple of key points that you're able to take away. So with that, thanks again for attending. Have a great rest of your Tuesday. Chris Jackson's back in 2 weeks at an hour earlier on Tuesday, 2 weeks from now. And he's talking about another case study about how to go about reliability engineering where it actually connects to a financial benefit in our systems. And so, and you can register up on Ascendo and see where the registration link is for that. And I'll be back on the second Tuesday next month, and I have no idea what I'm going to talk about. I have something drafted out, but that always changes, so I won't make any promises at this point, but I'll hopefully have it up later this week. So once again, thanks so much for attending. We'll see you in a couple of weeks for Chris's or next month when I come back again. And so once again, thanks, and we'll see you out there.